Thank you to Modal for that introduction. So thank you for citing me in the 1500s. Thank you to the organizers for inviting me, and thank you to all of you for being here. So good evening. Are you all ready to learn about the hilarious subject of computability theory? All right, well, let's get started. An algorithm is a sequence of instructions followed by a computer. Now, you and I are used to thinking of a computer as a machine, but originally a computer was a person, the person who executed the algorithm. Algorithms go back to Euclid's Elements in classical Greece and eponymously to Al-Khwarizmi in 9th century Persia. But it wasn't until the 20th century that we have a formal definition of algorithm when Alonzo Church, Kurt Gödel, and Alan Turing all made proposals within a year of each other. It's like buses. You wait 2,000 years for a theory of computability, and then 3 come along at once. Why did this happen? So as the 20th century dawned, David Hilbert in Göttingen was one of the foremost proponents of formal logic, and he had a program, not a computer program, but a program of work, and his program was to put all mathematicians out of business. Because what he wanted was an algorithm that, given a statement in formal logic, could decide whether that statement was true or false. So he wrote about it in this book, and it was called the Entscheidungsproblem, because it sounds better in German. A key assumption that Hilbert made was that logic was complete. That is, that if you had a proof of something, if you've proved a statement, it was true, and if a statement was true, then you could prove it. Now, he first published the Entscheidungsproblem, I think, in this textbook in 1928. No, it goes older, but this is the textbook from 1928. But in 1930, this man, Kurt Gödel, published his proof that any logic powerful enough to represent arithmetic is incomplete. And that meant that Hilbert was, forgive my use of a technical phrase here, screwed. So this is one of the earliest functional programs. It represents statements of logic and proofs of statement in logic as numbers using a clever technique called Girdle Numbering. It actually is a functional program that checks whether a particular number represents a proof of a particular statement. And by using all this machinery, he managed to write down a number that corresponds to this statement is not provable. Ooh. This statement is not provable. So if it's false, that means it's provable, and you proved something which is false, which means your logic is unsound, and that is a complete disaster. It means logic becomes useless. If it's true, then there must be a true statement that is not provable, and your logic is incomplete, which is not as bad as being unsound, but is still incredibly annoying, especially if you are Hilbert. So as soon as this proof came out, people began to think that the Entscheidungsproblem was undecidable. Now, as they thought it was decidable, then you wouldn't really need a formal definition of algorithm. You would just write the algorithm down, and it would be like Justice Stewart's definition of pornography. I know it when I see it, right? You could just recognize an algorithm by looking at it. But if you wanted to prove there was no algorithm for doing something, then you needed a formal definition. So the race was on. In Princeton, This man, Alonzo Church, wrote down the first definition, Lambda Calculus, in 1932. And in 1936, he put forward what's called Church's thesis, which says that anything that a computer can do, you can write down in Lambda Calculus. And he used it to show that indeed the Entscheidungsproblem was undecidable. So here is Lambda Calculus. It's the world's smallest programming language. This is the complete thing. It just has 3 constructs. And it's the world's coolest programming language because it was designed a decade before the first computer was built. For years, me and my friends my colleagues and friends, have worked on functional programming languages, which have Lambda Calculus at their core. And for years, industry has pretty much ignored everything we've done. Except now, all of a sudden, Lambda Calculus has become trendy, and you find it in C++ and Python and Java. Here is Duke, the icon for Java, looking very smug, because Java, along with Python and C++, now has Lambda constructs. Well, congratulations, Duke. You finally caught up with where Church was in the 1930s. Yeah, you guys can applaud that. So Kurt Gödel came to visit Church at Princeton, and he thought that Church's solution was thorough. His precise words were thoroughly unsatisfactory. So Church challenged Gödel. He said, well, you come up with your own definition, and I'll show that mine is as good as yours. And Gödel did this. He came up with a second definition of algorithm, what we call now recursive functions. And this was written up with attribution by Church's student Stephen Kleene. And Gödel and Kleene went off, Church and Kleene went off, and they proved indeed that the 2 definitions were equivalent. And Church went back to Gödel, and it's not recorded, but basically he said, so there. And Gödel said, oh, your definition is the same as my definition? My definition must be wrong then. The impasse was resolved by this man, Alan Turing, who was basically an undergraduate at Cambridge, and he came up with what we now call Turing machines. And the big difference in what Turing did from what Church did or what Gödel did is philosophy. Turing basically engaged in a bit of philosophy, saying, well, what could we expect a computer to do? Where here again by computer he meant a person, the person executing the algorithm. And he showed that a Turing machine would have all the capabilities of a computer. And Turing showed that his result was equivalent to Church's, and hence to Gödel's, and this finally convinced, Turing's philosophy basically, finally convinced Gödel that the 3 of them were correct. People often argue about whether mathematics is invented or discovered, but when you have 3 independent definitions that turn out to be the same, that is powerful evidence that you have not invented something, you have discovered a fundamental truth. It's not just sports fans that are impressed by a hat trick. Kurt Gödel was 28 when he undermined the life's work of David Hilbert, who was 68. Alan Turing was 23 when he resolved the argument between Alonzo Church, who was 33, and Kurt Gödel, who was then an ancient 30. So, to all you young people in the audience, you know what to do. Right? Please keep teaching your elders when we've got it wrong. Okay, that's computability theory. That's just the prelude. Now let's talk about propositions as types. So this man, Gerhard Gentzen, again at a very young age, he wrote his doctoral thesis, and in it he introduced not one, but the two forms of logic that we use to this day, the two most popular ones: natural deduction, which is what's written up on this slide, and sequent calculus, which we'll skip over by and large. He also introduced the use of upside-down A to mean for all. So again, for all you young people, there's another goal for what you can get done in your PhD thesis. So I'm going to take just two of these bits. So here's the definition of implication, and at the upper left corner there you have the definition of conjunction, ampersand, and here they are written out in modern notation. You'll notice that modern notation looks exactly like Gentzen's notation. The only difference is that he writes his letters in German, and I've written mine in English. So let's look at what this means. How many of you are familiar with basic natural deduction? Okay, about half of you. So we'll do a quick refresher course in how natural deduction works. So this says, so this formula here is read A implies B. If A is true, then B also must be true. And that backwards-looking C is a backwards-looking C. It stands for consequence. B is a consequence of A. And how would we know that A implies B is true? Well, assume A is true. And if assuming A is true, you can prove B, then that means that A implies B. So this is called an introduction rule. This is how we construct a proof that A implies B. How do we use or deconstruct a proof that A implies B? Well, if we know A implies B, and if we have a proof that A implies B, and we have a proof that A is true, then we have proved that B is true. Because if you know A and you know A implies B, then you may conclude B. The rules come in pairs. They're labeled with an I and an E. I stands for introduction. That means it's a way of constructing the given kind of formula. E stands for elimination. That means it's a way of deconstructing or using that kind of formula. And this was Gentzen's key insight, is that the proof rules come in pairs. They had formal logic before, but Gentzen was the first one to formulate things in pairs. So let's see how that works for a different connective. Conjunction. So if you can prove A and you can prove B, then you can conclude that A and B is true. You've proved A and you've proved B, so both A and B hold. What do you know if you know A and B hold? Well, one of the things you know is A must hold. And of course, the other thing you know is that B must hold. So again, these follow the pattern that the introduction rule constructs the relevant construct, in this case a conjunction, and that the elimination rules get rid of. So given A and B, we get rid of it to get A or get rid of it to get B. By the way, if there are questions, this is technical material people should ask. Are there any questions at this point? You shouldn't be afraid to ask questions, because I'm sure other people will have the same question. But I will press on, but do stop me with a question if you have one. Oh, I know how to check. Nod if you followed what I just said. Okay, enough people are nodding. Tony Hoare isn't, but... So here's an example of a proof. What I want to prove is that if I know B and A, it implies A and B. So to use a technical phrase again, this is what we call bloody obvious. But if it's bloody obvious, then there ought to be a proof of it, right? If we couldn't prove something as obvious as this, there would be something wrong with our notion of proof. So let's check that we can prove this. So remember, the way you prove an implication is by assuming the hypothesis. So let's assume B and A is true. Well, what do we know from that? Well, we can conclude that A is true. And from that, we could also conclude that B is true. And, oh, I've got proofs of A and B, so I've got a proof that A and B is true. And now I can discharge my hypothesis And so without assuming anything at all, I know B and A implies A and B. So there's a simple proof for you. Now, the reason that Gensen wanted to put the proof rules in pairs is so that he could simplify proofs. He wanted to get rid of roundabout proofs. In particular, he wanted to show something called the subformula property that says that if you have a proof, then the only formulas you need in it are your hypotheses and your conclusion and any subformulas of those. The reason that he wanted this is one of the things that follow from this immediately is say you have a proof of false with no assumptions. Then a proof of false with no assumptions would have to consist of false and all of its subformulas. So the subformulas of A implies B are A implies B and B and all of their subformulas. In other words, the parts of the formula. And the same for A and B. So what are all the subformulas of false? It has no parts. There aren't any. So there are no parts to false. Trying to construct a proof of it, you would just look and say, okay, so there has to be a proof that only uses false and the parts of it. Nope, there are no rules that look like that. There's no rule that has false on the bottom and nothing on the top. It's a lot like, what part of no don't you understand? So that gave him a very simple proof of consistency, as well as this much stronger idea that you didn't need any roundabout proofs. So how did he get rid of roundabout proofs? Well, the idea is, if you have this is why the rules come in pairs. If you have an introduction followed by an elimination, you can get rid of it, right? So this says, how do we know A implies B is true? Well, assuming A, we proved B. But then if we have a proof of A, we can conclude B. Well, yes, because instead of assuming A and proving B, I've got a proof of A right here. So I just use that proof of A, and then from that prove B. Now, note, so this is a simpler proof in that it doesn't introduce A implies B. It might be a much larger proof, because what the dots don't show you is how many times this assumption is used. Remember, here we used it twice. So you might copy this proof many times to get a bigger proof, but it will be simpler. Similarly, if from a proof of A and a proof of B, we can then prove A and B, and from that we conclude A. Well, there's a much simpler way of doing that, right? We proved A directly, just use that proof. So you can simplify proofs. And that guarantees the subformula property, and that guarantees things like consistency. But let's see an example. So here's the proof we had before, that B and A implies A and B. And let's say somehow that I've proved B and proved A, so I know B and A. So now, by the elimination rule, I can conclude A and B. But as you might guess, this is a more complicated proof than you need. And indeed, if we look, we see, oh, there's an implication followed by an elimination. So we can simplify that. The way we simplify it is we just take this proof and copy it, the two places where the assumption occurred. So if we do that, we get this. Right? We've just copied that to those two places. And now we have this. And notice that we've copied this introduction on top of this elimination. So you have an introduction followed by an elimination. And we can simplify that. So here we've got proof of B, proof of A, B and A conclude A. Just use the proof of A. Similarly, here we can just use the proof of B. And there is our simpler proof. So you can see this one involved things like B and A implies A and B, which are not subformulas of A and B, but this one just involves A and B, and it's two subformulas A and B. So we've established that the subformula property is true. Congratulations, you've just all proved something deeply profound. The trick, by the way, is knowing that this process always terminates. That's the hard part of the proof. And I'll skip over that, but you can show that this process always terminates as long as your formulas are finite. Okay, so that was Gensen in 1935. Now remember, Church had his Lambda Calculus, and he originally introduced Lambda Calculus as a kind of macro language, for those of you that remember what macros are, for writing down formulas in logic. But when he did it, he realized it was sort of powerful, and he said, there may indeed be uses of the system other than its application as a logic, which turned out to be profound because it turned out to be a model of algorithms, as we saw. But also it turned out that using it as a logic, it was too powerful. Because using lambda terms, you could in essence write down formulas that were infinitely long, and then the subformula property doesn't apply, and it turns out that your logic is inconsistent. By using an infinitely long formula, you can write down a proof of false. So for a logic, this is bad news. So lambda calculus was a huge success, right? It was a model of computation. Except, just as now people sort of look askance at functional programming, right? You saw Girdle's response. Everybody's response was like that. They didn't like lambda calculus. They thought, oh, recursive functions, those are good. Well, Turing machines, we like those. Lambda calculus was sort of pushed to one side. But Church still wanted it as a model of logic, and so he used Russell's solution for getting rid of paradoxes and added what are called types. So now the things in red are formulas of lambda calculus, and I've extended lambda calculus. Remember I said it had just 3 things, so this one has just 5 things. So in addition to lambda expressions, we can also build pairs and extract the first or second component from a pair. And let's look at the typing of that. So if M is a term of type A and N is a term of type B, then the MN pair is a pair whose first component has type A and whose second component has type B. And if L is an AB pair, we can extract its first component, which of course will have type A, or its second component, which will have type B. If X is a variable of type A, and using X I can build up a term, N, of type B, in which X appears free, then I can write lambda x dot n, and I've now bound my free variable, and lambda x dot n stands for a function from A to B. And of course, if L is a function from A to B, and M is a term of type A, then L applied to M, the result is of type B, the result of applying the function. Clear enough? Any questions? So here's a simple example of a program to give you an idea of how this works. So lambda z of the pair second of z, comma first of z is a function. And if z is a B and A pair, it returns an A and B pair. And all it does is it swaps the 2 elements of the pair. So it builds a new pair whose first component is the second component of z, and whose second component is the first component of z. So it just swaps the 2 parts of z, and you can sort of see that from the type, right? It takes a B and A to an A and B. And here is the proof that this function, lambda z, second of z, first of z, is well typed. So assume z has type B and A, then second of z has type A, and first of z has type B, and then the second z, first of z pair has type A and B, and then lambda z, second of z, first of z, is a function that given a B and A returns an A and B. And you can evaluate programs. So how do we evaluate lambda xn applied to M? Well, it's a function, and this says if M were the value of x, return n. So we just do that. Everywhere that x appears there, we replace it by m, and we compute n with every instance, with m replacing every instance of x. So we just do a substitution to do computation. And I'll show you an example of that in a minute. And then if m is a term of type A and n is a term of type B, I can form the pair mn of type A and B, and if I take the first of m and n, what is that? It, of course, is just m. And similarly, second would be just n, but I've not written that down. So as an example, here's our program again. So this is steps evaluating a program, and in fact, if it's well typed, we are guaranteed that these steps will always terminate. That unlike for algorithms in general, the halting problem is solvable for typed programs. in fact, the halting problem is trivially solved. All typed programs halt. So this is fantastic news. All typed programs halt. It's also worrying news. It says, okay, that means typed programs cannot do everything that a Turing machine can do, because they always halt. My friend, my colleague Connor McBride, hates it when I say this. He says, no, 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 you can also do it typed. You just keep doing it until you're tired. And then you can compute anything that you could compute otherwise. Just set the number of steps that you're willing to do in advance, and then you can do it in a typed way. But nonetheless, I think there's fundamental trade-offs, which we as engineers appreciate. Untyped lambda calculus, you can compute any computable function. Typed lambda calculus, very powerful, but cannot compute every computable function. It's guaranteed to terminate. And the first proof of that, in fact, was written out by Turing. So let's look at evaluating a program. So on the left, there is the program we had before. And on the right, I've just built a YX pair. And then I take my swap function and I apply it to a YX pair. So what do I do? Well, I substitute YX pairs for Z. So the next thing is just I've substituted YX for each occurrence of Z in the thing above. And notice, so the first time, notice that I've got a function introduction followed by a function elimination. Now I've got pair introduction followed by pair elimination. And so I just need to compute what is the second component of YX and what is the first component of YX. And they are, of course, just X and Y. So now we have evaluated our program. Okay, at this point, I'd like you to stop and reach under your seats. You should find a pair of rose-colored glasses there. So please put on the rose-colored glasses. You will then not see red. You will only be able to see blue. And when you do this, you will all go, aha, because you will have noticed that the first set of slides I presented for logic and the proof of the subformula property, and the second set that I presented for lambda calculus and how you go about evaluating programs are identical. You may all now say, ooh. So this is a very deep idea. This is a very shallow expression of that very deep idea. This is a nice picture due to Luca Cardelli, which he called the Curry-Howard homeomorphism. But if you think about the deeper idea in logic, it's often called the Curry-Howard isomorphism. And this is because a form of it was written down by Haskell Curry, and then something very much like what I just showed you was written down a bit later by William Howard. In this paper, so he first circulated as Xerox notes in 1969, and then in 1980, in the Curry Festschrift, he published this paper laying out very neatly, in much the same way I've shown you, the correspondence between natural deduction and lambda calculus. So this is sometimes called the Curry-Howard isomorphism or the Curry-Howard correspondence, and other people call it propositions as types. Other people notice that many other people, like Breuer, it's sometimes called BHK because Breuer, Harting, and Kolmogorov, the intuitionists, had very similar ideas to this already back in the 1920s. De Bruijn, in the early 1970s, started implementing computer programs based on these ideas for doing proof checking. So many people contributed to these ideas. So although many people call it the Curry-Howard correspondence, I now think the least controversial name is propositions as types. And this indeed is the name that Howard uses. And you can see that in this we have not just propositions as types, but also proofs corresponded to programs, and normalization of proofs corresponded to evaluation of programs. So you get all three steps. So it's not just a shallow idea. There's a lot of structure that is preserved by this correspondence between logic on the one hand and typed lambda calculus on the other. So you now are probably all thinking the same thing I thought when I first saw it, which is just, oh, that's kind of cute. That's just, you know, sort of an accident that those two things look a lot like each other. But it doesn't just happen once. It happens again and again and again. There are many different formulations of logic and many different kinds of logic, and pretty much every one of them that you can name corresponds to, every one of them that you can name corresponds to an interesting form of computation. So the original instance of this is Genson's natural deduction and Church's typed lambda calculus, but the logician, Roger Hindley, in 1969, came up with type schemes for lambda calculus, and a little bit later, the computer scientist Robin Milner came up with the type system used in ML, which has been inherited by pretty much every other functional language that's typed, including Haskell. And nowadays we call it the Hindley-Milner type system. But there were two independent inventions of the same idea, once by a logician and once by a computer scientist. Similarly, the generalization of the idea of type schemes is type abstraction, and this was formulated as something called System F by the logician Girard, and as polymorphic lambda calculus by the computer scientist John Reynolds. Again, the logician gets there a bit before the computer scientist. The same thing happens, modal logic. There are many, many different kinds of modal logic, and pretty much every one of them corresponds to an interesting computational idea. And one in particular corresponds to monads, which can be used to model things like state and exception in functional languages. And it was very nice of Bodil to say that I invented monads, but that actually goes to Leibniz, and the use in category theory, which we inherited in functional programming, is due to Eugenio Maggi. Girdle did this amazing embedding of classical logic in intuitionistic logic, which really pissed off the intuitionists, by the way, because they were like, you know, intuitionistic logic is special. You know, you should use intuitionistic logic, not classical logic. Classical logic does too much. And then he showed, no, everything classical logic does, you can do inside intuitionistic logic. In particular, he showed that the formula A is true classically if the formula not A is true intuitionistically. And then one of Girdle's proofs corresponds exactly to what we now call continuation passing style, which is a standard technique in functional programming. And then in 1987, Jean-Yves Girard again came up with something called linear logic, and only recently have Keres and Pfennig pointed out that, so Kohei Honda did something called session types. So these are types for writing down protocols that are used for communication among processes. And he was in fact inspired by linear logic. Two of his connectives come directly from linear logic, but the other two are just send and receive of messages, which clearly had nothing to do with linear logic. They were sort of just hacked in. And then in 2010, Louis Keres and Frank Pfennig said, oh, actually those other two that look like they're hacked in, they just correspond to tensor and par, the other two connectives of linear logic, which was amazing. And I'm really excited by this because obviously concurrent and distributed programming is the most important thing we have to do. And there are many solutions. Of course, the problem is there are many solutions. Which is the right one? So if there's one that actually corresponds to a logic, that might be a hint that that's an interesting place to look. Pretty much every functional language has lambda calculus at its core. So so understand, right? I've talked about the discovery of the formalization of algorithm, right? 3 independent discoveries. Now we have logic and typed lambda calculus, and again, they correspond. So not 3 independent discoveries, but 2 independent discoveries, and a very deep correspondence, as we saw, propositions as types, proofs as programs, normalization of proofs as evaluation of programs. So deep correspondence. So again, I want to make the claim that lambda calculus is discovered. Now, all functional languages have arbitrary bits that are very clearly invented. But all functional languages have at their core lambda calculus, which is discovered. So this is my invitation to you to use programming languages that are discovered. Most of you use programming languages that are invented, and you can tell. So this is my invitation to you to use programming languages that are discovered. The same ideas, as we saw, there's a correspondence to proofs, and as a result, lambda terms are a very convenient way of writing down proofs that facts hold. And so pretty much every automated proof assistant in the world, again, uses these ideas at their core. And so things like the proof of the four-color theorem that was done in Coq is all based at root on the ideas that I've shown you today. And these also turn into programming languages with advanced type systems, something called dependent types. So if any of you get interested in dependent types, it is the notion of propositions as types that led in Howard's first paper for him to propose dependent types. So let's conclude. So I talked about how Turing's contribution to a large extent was philosophy. So if you'll forgive me, I'm going to indulge in a little bit of philosophy to conclude. What would happen if we tried to talk to aliens? So this is not an imaginary exercise. We have done this. The spaceship Voyager has on its side this plaque, which is to talk to aliens if we ever find them. So on the left here, we've got a map of where you would find Earth. So the point in the center corresponds to Sol. The points on the outside correspond to different pulsars. There are marks on these, which correspond to binary numbers, which are the frequency of waves from those pulsars. And then the length of the line is the distance of the pulsar from Earth. And then on the right, you have a picture of Voyager with a man and a woman standing in front of it. And there's a schematic diagram of the solar system at the bottom. What would happen if aliens found this? So I think the bit on the left, they'd probably be able to work out what binary means. They probably are familiar with pulsars. They could work out what, and they would almost certainly work out that the length of the line corresponded to the distance between the point in the center and these different pulsars. So they could work out where we were. What about the bit on the right? Well, if Star Trek is correct, aliens will look at it and say, ah, they look just like us. Except they don't have pubic hair. But if Star Trek is not right, and aliens have a very different perceptual system, the bit on the right, they might just think, oh, that's indecipherable squiggles. We don't know what will happen. So some kinds of things are easy to communicate to aliens, other things might be harder. There's actually a film called Independence Day, where aliens are destroyed by a computer virus. Here's the computer virus. You can see that it's written in C. It's actually a dialect of C that only has open angle braces. And many of you, like me, might find the notion that you could give a virus to an alien computer written in C a bit far-fetched, right? Even if we just sent a program in C to aliens, I think it would be a lot like the thing on the right-hand side of that plaque, right? They might be able to decipher it, or they might not. It might just be indecipherable squiggles to them, as it sometimes is to us. But what if we sent them Lambda Calculus? Lambda Calculus, I think, would be more like the things on the left-hand side of the plaque. Almost certainly, aliens will have worked out natural deduction and logic, and therefore they must know about Lambda Calculus by the propositions as types, and therefore they would be able to understand, decipher a program written in Lambda Calculus. Of course, the symbols would be different, but they'd be able to work it out. So should we call Lambda Calculus the universal programming language? Well, let's ponder that for a minute. Some people have talked about multiverses. This is often used as an explanation of why the universe looks the way it does. Well, why is gravity enough to clump things together and make stars and planets? Why is the weak electron force just enough that things clump together into matter? Just a little bit greater or a little bit smaller, and that wouldn't happen. The universe would be very different. And some people say, well, there are lots of universes, and we're in the one that has matter and life. Multiple universes have gotten so much into the popular literature that I found them in books by Salman Rushdie, and this is from a play called Constellations. It has one of the best stage directions I've ever seen. You know, normally if you read the text of a play, it begins with this long bit in italic, and it says, okay, the stage has a house on it here, and there's a door there, and there's a table there, and there's a gun sitting there that's going to be fired in the third act, and on and on. This one has the best stage direction ever. It's just one line. It says, in the text, a horizontal rule corresponds to a change of universe. So it's a lovely place. See it if you get a chance. Anyhow, this idea that there are many universes comes often in popular literature and in physics and astrophysics. And Lambda Calculus, natural deduction, you might have a better imagination than me, but I cannot imagine a universe. I can imagine a universe with different gravity. I can imagine a universe with a different weak electric constant. I cannot imagine a universe where modus ponens does not hold. I cannot imagine a universe where we don't have natural deduction. I cannot imagine a universe where we do not have Lambda Calculus. So we cannot call Lambda Calculus the universal language. That would be wrong, because calling it universal is too limiting. So that's it. I'm done. I just want to conclude by reminding you that if you do have a tough job, then what you should think is that this is a job for Lambda Calculus.
I have a question. Before Girdle, here.
There are very bright lights shining in my eyes.
Before he proved that inciting problem is not decidable, were there more mathematicians like Hilbert looking for, ability to prove every problem with algorithms, with computers?
Yeah, so
Or was he the only one, the lunatic, trying to do it?
No. Everybody bought into Hilbert's program. It was extremely influential. Hilbert's work was extremely influential. And everybody just assumed that the Entscheidungsproblem would be decidable until Girdle dropped his bombshell. And then they changed their mind and they thought, oh, maybe it's undecidable.
So
that's what began the race, and that was why within a very short time of Girdle coming up with this result, you had 3 formal definitions of algorithm appearing.
So I wonder how many mathematicians were there who actually knew it. I mean, they were afraid to lose their job, but just didn't talk about it at the conferences or whatever.
So If he'd actually succeeded, of course, whether you could do the computations in practice was another matter. He just wanted to be able to do the computations in theory, just as the 3 definitions of algorithm that came up were rather inefficient. Nobody would actually want to compute with the Turing machine. Nonetheless, Turing's work and the other work had profound impact on the actual creation of computers a decade later, and Turing was one of the main people involved in that.
Okay, I have a question. I've read several of your papers, and I've also read this propositions as types paper, and it's really interesting and educational, like the introductions of many of your papers, which maybe the monads paper, all of these things, they have a lot of context, a lot of historical context, and I find it really interesting all the time to read this perspective from you. And I wonder, often when I'm reading these things, you know, you do a nice job of relating the history of computation to actually, you know, computers and computing things. I was just wondering if you have suggestions for anybody, whether or not you are a JavaScript developer or a PhD student in logic. Is there some sort of suggested reading that you could provide for, you know, the history of these things? Because other than the description that you provide, I find, you know, many things describing things in the wrong direction. I find a lot of your descriptions very nice. So I was just wondering if you could provide some recommendations for things to read for anybody.
Okay, I'm supposed to repeat the question. The question was, I've read lots of your papers and they're very nice. And then it went on to mention there is a paper of this talk called Propositions as Types. You can download it from my website. It will also appear, I'm told, in Communications of the ACM in December. So if you want more details or you want to go over it again more slowly, have a look at that paper. And then Heather asked, what else should I read on this subject? So there are several citations in that paper for people that want to follow things further. So I recommend those. I think one thing that I didn't mention is the preface to Girdle's collected works, which describes Girdle's life. Let me try that again. The preface to Gensen's collected works, which describe Gensen's life. It omits a couple of minor details, like that he was a Nazi. But he pissed off his fellow Nazis because he wanted to learn logic. So he studied logic from Hilbert and from Hilbert's assistant Bernays, a Jew. So they didn't trust Gensen. And when the war started, they shipped him off to Prague. And then when the war ended, the Allies marched into Prague. They locked up all the Germans, including Gensen, who wrote, this is okay. I will have time to complete my proof of the completeness of second-order arithmetic. But they forgot to feed the prisoners, and he died of starvation at a very young age. So that's another interesting part of the story, and you can find that in the introduction to Gensen's collected works. And it was reading Gensen's original paper that sort of got me into understanding what this correspondence was about. So I highly recommend to everybody here, if there's anything that you like that's interesting, for goodness sakes, go off, find the original paper, and read it. Right? You don't want to learn about things like pre- and post-condition proofs from the people writing about it today. You want to go off and find Tony Hoare's original paper and read that. And similarly for anything else, for other people not sitting in this audience. So I strongly urge you, go off and read the originals. They are wonderful. So just any bit of computing that you like, Heather, just go off and read the original. That's well worth doing. And then my final recommendation to you about what places to understand the history is there's a lovely book called Logicomics, which goes through the history of Russell and Cantor and so on. And it's a bit over the top sometimes, but generally it's pretty good. I highly recommend that. And if you want to learn about the history of Turing, of course, read Andrew Hodge's book. Do not watch The Imitation Game. Yes. Yes.
So looking at the list you had, it always seemed that the mathematicians found the things before computer scientists. Why do you think that is, and do you think that it will ever go in the other direction?
So there's actually one counterexample here, which is linear logic. The paper on linear logic is massive, and the mathematicians were having trouble refereeing it. So it got published in Theoretical Computer Science with a little note at the beginning saying, this is very important, I'm publishing it without it having been refereed by the editor. So linear logic was already known at the beginning to be of direct relevance to both mathematicians and computer scientists. And then, as I said, when Kohei did session types, part of it was based on ideas from linear logic. And then much later it turned out, oh, it exactly corresponds to linear logic, which was a surprise. But Jean Reynolds, who I mentioned was the other guy who was just behind Gerard for doing polymorphic lambda calculus and the basis of data abstraction. So all abstract data types basically trace back to those papers by Gerard and Reynolds, which again are well worth reading. But Reynolds, it turned out, had done something called syntactic control of interference, which was about trying to tame concurrent processes, published a few years before linear logic. And it's not identical to linear logic, but there are close relationships between them. So people sometimes call syntactic control of interference Reynolds' revenge. So just once, the computer scientists sort of beat out the logicians. But basically, the logicians always get there first. They've been doing it for much longer.
So since there's this correspondence between computational models and logic systems, the natural question to me is the untyped lambda calculus, what sort of logic system does that correspond to? Or is it just an inconsistent one?
Oh, very good question, right? What logical system does untyped lambda calculus correspond to? It turns out that you can make a close correspondence between untyped lambda calculus and Curry's paradox, which is a way of proving false using an infinite formula. So I'm not going to go into the details here, but there actually is a correspondence. And this also lets you then, in a logical way, bring back the full power of recursive function theory into typed lambda calculus. Remember I said typed lambda calculus always terminates, but once you add back in recursion, which you can do in a logical way using Curry's paradox, you get back the full power of computation. And this is why all the functional languages I mentioned, in fact, are Turing complete, because they support recursion. So this is, I think, the most it's a great question, because this is, I think, the most interesting aspect of propositions as types, which is it's so powerful that it doesn't just work for every logic, but even for places where logic breaks down, for paradoxes, it does something interesting there as well.
So I have a question. You keep talking about this computer science thing. Do you think it has any application to general knowledge?
Do I think computer science has any relationship to general knowledge? That's a very interesting question. I think we've seen how deep computer science can be. We often think of it as, oh, I'm just hacking away. I'm an engineer. And there's a lot of very interesting engineering in what we do. But there are also very deep ideas. How many people have heard the phrase computational thinking? Only a few of you. Okay, now you've all heard the phrase. Computational thinking stands for the notion that patterns of how information is processed are very important in understanding any natural science. And in fact, I don't work in a department of computer science. I work in the School of Informatics. And informatics was a name coined to capture the notion that ways in which information is processed are absolutely fundamental and universal, or maybe even more than that, and are very important in understanding, and people have used these ideas now in understanding physics, in understanding biology. Patterns of information processing are very important. And I prefer, in fact, the name informatics to the name computer science. There are only two things wrong with the name computer science: the word computer and the word science. right? The word computer doesn't really belong there because it's not about the machines. It's about processing the information. As Dijkstra has pointed out, calling it computer science is a bit like calling astronomy telescope science. But of course, the other thing that's wrong is with the word science. I profoundly believe that informatics is a science. And if you are a science, a real science, you don't need to stick science in your name. So let's stop there. Thank you very much. Let's go get a drink.